So here we've got three equally strong, equally massive astronauts, and they decide to play a game as follows. The first astronaut throws the second astronaut towards the third astronaut, and the game begins. Describe the motion of the astronauts as the game proceeds. Assume that each toss results from the same size push. How long will the game last? It will last one push, and here's why it will last only one push. If you have your astronauts, you've got astronaut number 1. He has astronaut number 2 within his grasp here, and we have astronaut number 3. This astronaut number 1, here's number 2 and number 3. Astronaut 1 pushes astronaut 2. When that happens, they both go away from each other at the same speed. That means astronaut 1 is going to be lost forever, because when astronaut 2 gets over to astronaut 3, astronaut 2 then hits astronaut 3, he stops, and astronaut 3 takes off at the same speed astronaut 2 then went in the opposite direction. So when the problem's all done, here's astronaut number 1. He's moving in this direction at this speed. Astronaut 2 is stuck in the middle. He can't move at all. And astronaut 3 is now stuck going in the opposite direction at the same speed, but in a different direction than astronaut number 1. It's not a very fun game, especially if you're in outer space. You would be stuck forever, and that would be really, really bad. The very next thing that we can look at is 2D collisions. We know that the momentum in the x direction has got to be conserved, and same thing in the y direction. We're going to treat the x and the y coordinates independently, so we ignore x when calculating y, we ignore y when calculating x. This is a good example problem. It says calculate the velocity of an 8-kilogram ball after the collision. So we have a 2-kilogram ball that's moving to the right at 3 meters per second. It makes a glancing blow, hits the 8-kilogram object that's not moving at all, and when it does that, the angle between the two is about 50 degrees. No, you actually have an angle here of about 50 degrees. So what they essentially want us to do, let's just make sure we clarify the angle. The angle here is 50 degrees. We don't know what the angle that the second object came off at is. Went ahead and did this problem so that I can do a little bit better job of going through what's happening. In the x direction, the sum of the momentum before should be equal to the sum of the momentum after. We only have momentum for the first object, and we know that its mass is 2, its speed is 3. For the first object after, in the x direction, we notice that its speed in the x direction is due to that 50-degree angle. So we're looking for this line right here, knowing that this would be 2 meters per second. So if we're looking for this side and we know the angle's 50, we're going to say 2 times the cosine of 50 plus 8 is the second mass, and we don't know what the speed of this object is in that direction. So we can say v2, the after in the x direction, so the speed of the second object afterwards in the x direction is 0.43 meters per second. So I know this object is going this way at a speed of 0.3 meters per second. For the y direction, we've got the sum of the momentum before should be equal to the sum of momentum after. There is nothing going in the y direction at all to begin with, and then we do have speed in the y for both of the objects, or momentum for both of the objects in the y direction. Once again, we need to this time look at how fast is number 1 traveling after the collision. Based on the fact it's going 2 meters per second in this direction, we need to find out what is the speed in the y. We can very easily do that just by taking 2 times sine of 50. Then we can add that to 8 times v2ay, because 8 is the mass of this object, and v2ay would be the speed going from top to bottom. If you solve this equation for the v2ay, for the speed of the second object afterwards in the y direction, we get negative 0.39. So this speed is negative 0.39 meters per second. If I want to know what the final speed is, I've got to do a little bit of use the Pythagorean theorem. We can say that the final speed would be equal to the speed in the x squared plus the speed in the y squared, and you end up with a final speed of 0.58 meters per second. So this long line right here this long line, oops, this long line that you see, this long line right here should be 0.58 meters per second. We do know the speed in the y, we know it in the x, so we can use the inverse tangent of the y divided by the x, and we end up with negative 42.2, and that would be this angle right here, 42.2 degrees. And it's negative because it's moving from the horizontal down. And you would not need to put south of east on that one because of the negative sign itself. And that is the end of the sample problem.